Okay, good afternoon, everyone. My name is Rez Mani, and I work for the company Allied Scientific Pro. The title of today's webinar is Laser Cleaning Method and Case Studies. So this webinar is being recorded, and the recording will be sent to you within a few days. We also have a Q&A session at the end where you can ask questions, and my email is also given here in case you have any questions. So I've given this webinar a number of times, and every time we try to modify the content so that it reflects the activities of the company, so it won't be repetitive for those who are attending this webinar for more than once. All right, so what we are going to talk about today is, first of all, the introduction to laser ablation. So laser ablation is a more general than laser cleaning. Laser cleaning is a subset of laser ablation that contains, laser ablation could be drilling, scribing, cutting, many different applications. So laser cleaning is one of those applications of laser ablation. So we also will talk about types of lasers used in laser ablation, and then also other competing surface cleaning methods. We will compare laser cleaning with these other methods, and then we will go into the physics of the laser ablation, talk about material removal efficiency, and what is the important laser parameters and material property parameters that are there. Then we would look at different time zones for lasers, femtosecond, picosecond, and nanosecond regimes, and how they are different from each other. We would compare Galvo and Polygon scanners, and then we will go into some applications, such as aviation, the nuclear industry, and also case studies where we have done work with the laser cleaner, such as Perma-Fix nuclear decontamination facility testing in Richland, Washington, Irving shipyard results, which is brand new. We never talk about this. This has been done only 3 weeks ago. And then testing at Canada Aviation Museum, removal of leaded paint, polygon scanner use, removal of weeds, and laser cleaning in food industry, and cleaning of bacteria. And so this will be the outline of our talk. During the webinar, I will also give maybe a few videos. I'll share some videos with you. I'll share the link because sometimes there's a lag when we are sharing the video. So if you want to play it on your own browser, that's fine too. So what is the principle of laser ablation? Basically, the main idea is that a laser beam is focused on the surface, and that generates a high heat, high temperatures, and high temperature gradients. This would cause high mechanical stress, and a plasma is formed if the energy is above a certain level, which creates a shock wave, and the shock wave will cause the mechanical breakdown of the surface. So we would mostly talk about pulsed lasers because you could control their parameters much better than continuous wave lasers. For continuous wave, you only have the wavelength and the power, but for pulse lasers, you could control the pulse repetition rate, the pulse duration, energy per pulse, and so on. So we would mostly focus on the pulse lasers for ablation and cleaning. So here's a paper that shows again basic principles of laser ablation. This is from a Malaysian author in automotive industry. So you can see there are coatings in the automotive industry on the metal substrate. These coatings are mostly consisting of resins, pigments, solvents, and additives. So the laser beam is focused on these coatings, and it just creates a shock wave and crack network, and then this shock wave would blast the coating. So this is the case where the coating is actually absorbing the laser radiation. And there are also other cases where coating is transparent, but the laser beam passes through the coating and is absorbed by the metal underneath. And that generates a shock wave and removes the coating. So in that case, we call it spallation. That's a different way of removing. And we'll talk about that when we go to a nuclear industry. So these are some of the lasers that are used for laser cleaning and ablation. Starting from the UV laser, excimer laser is shown here, and you can see that this is not actually meant for field use. It's more for lab use. It's not rugged. It's actually low rep rate, and there are several discrete wavelength: 193, 282, 351 nanometers. It's for used for germicidal applications and photo dissociation applications. So it's a gas laser basically. The medium of uh, emitting is a gas. Then we go to the CO2 laser, another gas laser at 10.6 micron. It's very popular for industry, for cutting applications, and also for cleaning applications for the reasons that I'll mention later. So this laser requires some significant cooling. And then we go to solid state lasers, neodymium YAG laser at 1064 nanometer, which can also we can also generate the second harmonic, the fourth harmonic at 532 and 266 nanometers. This has many applications for cleaning, for LiDARs, for so these are the two basic applications: LiDAR systems and laser cleaning, also for research purposes. And finally, we have the Ti Sapphire laser, which is a tunable near IR laser. It has to be pumped by an argon laser, and the range is 650 to 1100 nanometer. But it has a femtosecond pulse, which is low power for cleaning applications. But the most important and most popular laser for cleaning is the fiber laser. Well, we tend to think that it's fiber laser because neodymium YAG laser and CO2 lasers are also used for cleaning. But we like fiber lasers because in this case, you don't have mirrors for the laser, and instead you have some, you can say, fiber Bragg gratings, which is some scribing that you can see inside the core of the fiber. And this way, uh, the wavelength is reflected from this grating. A particular wavelength is selected and is reflected back into the core. So you don't have to use mirrors. You can just get the amplification by a reflection from these fiber Bragg grating uh, structure inside the core. And this is very useful because fiber laser is very flexible. It could reach hard to reach places. For example, for CO2 laser, it's not that simple to direct the beam. You need a system of mirrors or you need robotics. But this one, you can flex it and you can shine it anywhere you want. Uh, there are also other advantages, which include high pulse energy, high average power, good beam quality, and variable pulse length. This laser, fiber laser, is pumped by a diode laser. So now let's go back again to laser cleaning, which is a subset of laser ablation. So absorption of a laser radiation causes rapid heating of the surface, and that in turn generates a shock wave, blasts the contaminants of or the coatings from the surface. So here you can see our 100-watt laser system. It's the laser box that you can see over here where the pumping takes place. There's a fiber optic cable, there's an isolator, and this is the laser head, which contains the galvo and also the lens. So to get a better understanding, let's look at a particular cleaning application where rust is being cleaned at a metal surface. So what I will do is I will share that with you. So this is, I'll send it so you can actually uh, basically play it if you like in your browser, and I will also play that. We So here you see the plasma that is generated. This is the plasma, and this is the vacuum pump that removes all the debris. The rust is being cleaned. Okay, so that was that. Let's go back again to uh, our presentation. All right, so next, this laser cleaning is used in many different applications for conservation, restoration. For example, we have cleaned the Parliament building in Ottawa. Then you also have for aerospace, automobile industries, and ships' body parts. I'll get to that in one of our case studies. And also in industry, nuclear power plants, hydroelectric plant, power plants, aluminum plant, and so many food plant also. You could use this laser cleaning. So what are the important parameters for laser cleaning? First of all is the wavelength, which is quite important because some of the wavelengths are heavily absorbed and some of them are not absorbed. So if you look at, for example, near IR, it's very well absorbed by metals, but the mid IR is reflected by metals. But for plastics, near IR is not absorbed that well, but mid IR is absorbed very well. So also for paint. So one may tend to think that it will be good to use the mid IR laser for cleaning paint from a metal surface because the paint absorbs the mid IR very well and the metal underneath reflects it. So that means no substrate damage. So this is true, but the issue of guiding the beam and not being able to uh, basically couple it into a fiber optic is a big issue. And then we'll also talk about some other advantage of near IR. I'll get that to that later. So then there's pulse width or pulse duration. So larger pulse duration will have a larger thermal penetration depth, so it will cut deeper. So they require higher energy per unit area or fluence to ablate the material. So the pulse duration is a factor that you have to take into account, especially if you don't want to damage the substrate. Then there's a pulse energy. Of course, more higher pulse energy would uh, uh, increase the rate of ablation. The beam shape, depending on what you're cleaning, if you're cleaning a historical structure with lots of nooks and crannies, you want to use a smaller beam so that you can clean very small areas, complex shapes. But if you're cleaning a wall or a body of a ship which has no structure, you want to use a longer linear beam so that you can cover more area and do it faster. A repetition rate also of the laser is important because higher repetition rate increases the depth of ablation due to heat accumulation. So the same pulse energy, higher repetition rate, you can cut deeper, you can remove more of a layer of paint or contamination. There are also other important parameters. The scan speed, if you increase the scan speed, the depth of a crater would decrease because the dwell time is less. Number of passes also plays an important part. Increasing number of passes increases the ablation rate. Now, also you have to take care of the temperatures. For example, in this graph, in Shamsu Joha paper, uh, which is an author, uh, I think he's a Malaysian author, you see that when the fluence is below 3 joules per centimeter square, there is no heating. The temperature is below the melting point of the steel. This is for a steel substrate. But as soon as the fluence rises above 3 joules per centimeter square, there's a big increase in temperature and melting takes place in the substrate. So that's important. Now, we also look at other methods of cleaning surfaces. Uh, so these methods I can see from left to right: mechanical abrasives, chemicals, where you apply a chemical and then you wait and then you will scratch the coating. And then there are other methods where you have some kind of secondary material coming out of a high pressure nozzle, such as dry ice, which is CO2 pellets, sandblasting. We have grits and sand coming out of this nozzle, or water jetting, where water is coming out. And all these methods, they have a few drawbacks because, first of all, they contaminate the environment. You can see all this paint, and which could even be lead paint, something toxic, would go into environment and could potentially even go into water supplies. And the workers need heavy personal protection equipment because the secondary medium could bounce back and hit them, basically. And and these cannot be automated. There are environmentally unhealthy methods, basically, and they could also potentially damage the substrate, like especially mechanical abrasive and sandblasting. They could damage, and chemical methods could damage the substrate. So uh, these are drawbacks of these methods, plus that there are some of them are very noisy. On the other hand, laser cleaning is a non-contact method, so you don't use a secondary medium at all. The only thing that is hitting the surface is photon. So it has low environmental impact because the debris are collected by a vacuum pump on the spot. And one great thing about laser cleaning is the selectivity of it. And I'll show you a video where it becomes very clear what the selectivity means, that certain parameters such as pulse width, wavelength, and rep rate can be tuned to suit some material better, and also pulse energy, which I should mention in here. Localized action, versatility, controlled removal. Only center controlled thickness can be removed. So let me show you a video here that shows the selectivity, and this video is about a Coke Zero can where we are shining our laser beam on this Coke Zero can. So I will send you the link for this, and you can play it if you like in your own browser. Okay, so here you see there's a Coke Zero can, and the laser is shining on it, and there's black, white, and red uh, on the surface. But the laser is only removing the black paint, although basically you can see that although it is also shining on the red and the white. It's not removing them. And the reason for that is the absorption coefficient of the black paint is higher than the red and white. So if you tune the laser energy, the fluence, so that it's above the black absorption, absorption coefficient, and it's below the red and white, it will only remove the black, although it's shining on the white and red. So that is a very big advantage that other methods could not have. Sandblasting can never achieve that. It will remove everything. So this is the selectivity of the laser beam that is shown here. Okay, so we would stop this and go back again to our presentation. Next, what is next? Yes, so we talk about the advantages of laser cleaning. We need to also talk about some of the disadvantages because no method is complete. One disadvantage is the need for focusing. So for other methods, you could keep, for example, the nozzle at any distance from the wall that you're cleaning. But for laser cleaning, you need to focus the beam on the surface at a certain distance. And at that point, you hear extra noise, extra light is emitted, and fumes are emitted. So this is a requirement for laser cleaning that is doesn't exist for other methods. And also, when you compare the cleaning speed of laser cleaning, it is lower than the sandblasting. Of course, you're not considering the time that you have to spend for sandblasting to prepare the environment and also clean up after. But if you only consider the time of uh, cleaning, sandblasting is faster than laser cleaning. So in order to address these shortcomings, we have designed certain accessories, and one of them is this fume extractor nozzle. So you can see it has wheels on one side and there's an opening on the other side. So the laser head is fitted inside on the left on this opening, and then you would roll these wheels on the surface where you want to clean. So this way the focal distance remains constant, and you don't have to worry about adjusting the distance with your hand. And you can also remove the debris using this uh, tube that goes to the vacuum pump. Here is another case where you can even carry the pump on your back and basically use this roller to clean. And we also have robotics. Robotics control is very important. It could keep the distance constant and could do it more precisely and faster. So I will show you a video of this. Yes. I'll show you a video of the robotics. So here is the video of the robotics, which I will share with you. And I will also play it. So here you can see the robot is cleaning the rust from this pipe. It's controlling the distance of the laser. Maybe if we start from the beginning, you see it better. Yeah, this is the robot. Okay, so that was it. Next. There are also two small videos of comparing sandblasting with laser cleaning. Here I'll show you a video of the sandblasting cleaning a ship, and also laser cleaning a ship. Same thing. So I'll just go here and send you these YouTube videos. This is the sandblasting. I'll see. And I would also play it. You can see here the worker is wearing heavy personal protection equipment, and it's quite noisy, and all the debris is going into the environment. It's cleaning the body of the ship. This is a sandblasting method. On the other hand, you would also have the uh, laser cleaning method. I'll send you the link. I won't show the water cleaning because it's kind of similar to sandblasting. So I'll send you that and I'll also play it. And you can see here it's much neater. The laser cleaners keep cleaning the body of the ship, and this thick tube here is removing all the debris on the spot, so none of the contaminants is going into the environment. Okay, so that was that. So next, we would move on to physics, the physics of laser cleaning. So what are the important material properties and laser parameters that we should consider when we want to clean a surface? The optical attenuation coefficient, alpha, is depending on the material, is quite important. So the optical penetration depth is just 1 over alpha, and that's L alpha. Then you have the thermal diffusivity in millimeters square by second, the heat of vaporizations in joules per gram, and basically for laser you have type of the laser, wavelength, the pulse duration, the fluence, energy per unit area, and the beam size are important. So this diagram shows an optical beam that is hitting this block, and it penetrates by the length L alpha shown in orange here. So if the pulses is less than 10 picosecond, then you can say that this length that is 1 over alpha, and the thermal penetration depth is also the same as optical penetration depth. However, when the pulses are longer, is greater than 10 picosecond, the thermal penetration depth, LT, becomes longer than L alpha. It goes deeper into the material. And you can also calculate it from the square root of thermal diffusivity into pulse duration. So it depends on the pulse duration. The longer the pulse duration, the deeper the thermal penetration depths will be. And that affects the material removal efficiency, which is defined as volume removed per total energy. So in order to achieve ablation, we need enough energy to be deposited per unit area so we could ablate the material, and this fluence is called the threshold fluence. For pulses that are less than 10 picosecond, the threshold fluence is given by a product of density, heat of vaporization, and optical penetration depth. And it's independent of the pulse duration. But for pulses greater than 10 picosecond, um, this is given by rho HVLT, where LT is the thermal penetration depth. And that has a dependence on the pulse duration. So the threshold fluence increases with increases pulse duration. And this is something that you have to take into account, that you're cutting deeper and you need more energy with a longer pulse. Now we go into the different time regimes, time domains. If you go back again to ablation, which is a more general case, here is an application where it's like micro machining. You can see if there's a short pulse, there's a very neat and clean hole is being generated there. But if you use a longer pulse in a nanosecond, you can see all kinds of liquid physics effects are taking place. For example, you have damage caused by adjacent structures, surface ripples due to shock wave, surface debris, ejected molten material, and so on. So all these liquid physics phenomena start to appear when you go into longer pulses, which don't appear in case of short pulses. And here you can see a comparison of three regimes: 200 femtosecond, 80 picosecond, 3.3 nanosecond. This one is so neat and so clean, but for these ones, there's a lot of debris and melted areas around. So this is just a demonstration that uh, longer pulses have these effects. This is not meant to be said that we should not use a nanosecond, because all of our lasers are based on nanosecond, but I'm just trying to demonstrate that if you use very short pulses, the heat effect is less than when you use the longer pulses. Here also about the short and long wavelength behavior. Some graphs are shown here. In case of metals, we see that most of the metals show very low absorption at, say, 10 micron, the CO2 laser wavelength, but the absorption increases at 1064 nanometer. So higher absorption. But on the other hand, plastics and ceramic and glass, they have high absorption at 10 micron, and then at the neodymium YAG laser wavelength around 1 micron, their absorption decreases. So one has to take these into account. You also have the issue of galvo and polygon scanners. So when the laser power increases, the galvo scanners become heavier and heavier, and they slow down, so they can't keep up with the speed and the power. So for this reason, a polygon scanner has been designed that has multi facets. You can see it over here, and this rotates at a very fast speed. I'll show you a video later if I get a chance, and basically it will shine the laser on the surface. And you can also couple a CW laser to this polygon scanner, and it will do a very good job with the combination of CW lasers that sometimes are more readily available, and they're cheaper as compared to the pulse laser. They have fast scanning speed, lighter in weight, they have higher stripping efficiency, they could tolerate higher laser powers. They could use CW lasers, and the garbage removal is easier due to fast scanning speeds also. So we come to some applications here. Laser cleaning of aircraft parts, for example, is one of them. Here you can see the aircraft is in a hangar, and different robots are cleaning different parts of it. Probably this is CO2 laser because they're not using fiber optic. They're using many different robots to direct the beam at different parts. And one question is, why can't you have to remove the existing paint? Why can't you just uh, paint on top of it? And the answer is weight. You're increasing the weight by doing that. So you need to strip the old weight, the old paint, and then put a new layer. So the substrate damage is quite important in this case. One has to be careful not to damage the body of the aircraft. So you either use a CO2 laser or use a near IR laser, but tune the parameters very carefully so that it doesn't uh, basically damage the metal substrate. And then we come to the nuclear industry. It's a very interesting application in Ontario and Quebec. In Canada, we don't use coal for generation of electricity. And in Ontario, we use 60% of our uh, uh, electricity is generated by nuclear power plants, fission plants. And these plants, and this is one of them, they typically have a lifetime of 30 to 40 years. After that, they develop cracks in the structure, and they need to be dismantled. So because they are radioactive, the walls are radioactive, and you also need to recycle the metal tools inside that have been radioactive, then and pipes as well. Then you need to clean them. And a very good way of doing that would be to use a laser cleaning. So what happens in these reactors is this the corrosion of the metal pipes. It basically releases the products into the reactor coolant, and that gets circulated, goes into the active area, gets radioactive, it comes back and gets deposited on the pipes in the form of oxides. So these oxides are transparent to near IR wavelength, so one can clean them. Uh, the light passes, the energy passes through them, heats the metal, and then the shock wave is generated and removes the oxide very effectively. So basically, this is the same process of espallation that we talked about earlier. So now let's get practical and look at some of our uh, yeah, let's look at some of our uh, systems. And all right, sorry. Yeah, so let's look at some of our systems. So we have different systems. There is a 100-watt system that I'd already shown you with the rust cleaning of pipes, and this was our original system. And then a few years ago, we developed the 200-watt system that has a better form factor. It has some compartments where you can store some of the basically accessories such as goggles and lenses and things like that, because you can basically remove the lens, and there are three different lenses of different focal lengths that you can replace them for different working distances. So you can store that in the cabinets here, and this obviously has more power, 200 watts. We are also working on a compact 100-watt version. So this is 60% smaller and 40% lighter. And the idea would be that one worker could carry this unit. For example, inside a ship, you may need to go through different passages and hallways that are narrow or hatches that are narrow, so it's difficult to carry a big unit down there. So a portable unit will be definitely of use. It has an enhanced user-friendly interface. And then finally, we have our 500-watt system, which has up to 100 millijoules of pulse energy, the 1064 nanometer fiber laser. And you can see you can coil the fiber, which is up to 22. There's one unit that's 22-meter, the other unit 11-meter fiber cable that you can wrap a coil, and then it goes under this lid, basically stored very carefully and safely. And the laser head also is put there. It also has a separate chiller system for cooling the laser head, and also the the laser box. So let's now look at some of our case studies. Testing at Perma-Fix Nuclear Decontamination Facility in Richland, Washington. So we did go there, and this facility cleans intermediate and low-level contamination. And so we actually took our laser system there, and several objects such as concrete ecology block, a metal jackhammer, metal C-clamp, steel plate were cleaned. So the area of cleaning was under negative pressure, and the box was outside that area. Our engineer had a two-way communication with the engineers of the Perma-Fix. The radiation engineer would measure the before radiation, and after cleaning, he would measure after. So whenever the contamination went below 1000 dpm, then it was supposed to be clean. And in some cases, for example, for concrete, it took a few passes to get there, and some adjustments were required. And in case of metals, after maybe one or two passes, it just got there immediately. So let me share the video of this with you so you can take a look at the Perma-Fix operation, which is quite interesting. So I will send that and take a look, and I will also play that. Oh, sorry, this is not the one. Sorry, I have made a mistake here. I will send the right one, which is the YouTube video. Let's see. So let me share the YouTube video. The one I sent was just about Permafix. So this is the YouTube video of our operation. Before you use the app to control your Narwhal T10, they will. So 100-watt system. So here the metal is being cleaned, the metal plate. The engineer technician is cleaning it with our laser cleaner 100-watt system, and the radiation technician is measuring the disintegration per minute. And this tube goes to the vacuum pump through the HEPA filter, so collects all the debris. You can see that the laser head is all wrapped in plastic bags, so that it doesn't get contaminated. Here there's a C clamp that is being cleaned. It's radioactive, so after two passes with laser, it went down to less than 1,000. Initially, it was 5,000. Here you can see the body of the C clamp is being cleaned. There is a curvature there, and here is a torch head is being cleaned. It was 15,000 before, and after two passes, it was 4,000. And finally, there's a concrete block, which was the most difficult one. That's why it has a small beam, because there's kinds of pore structure. So there has all kinds of porous structure, which makes it more difficult to clean. All right, so let's go back again to our uh, presentation and get to the new stuff that we have done. So this is a brand new case study that I'm eager to talk about. This is about the laser cleaning in ship industry, and this has been done only 3 weeks ago. The trials were done in Halifax shipyards and also Shelburne Ship Repair, that both belong to Irving Shipping Incorporated, or ISI. So the idea was uh, basically the idea was to have a better cleaning method as compared to what they already use, which is the sandblasting. Um, so you wanted to have a better method to reduce the cleaning time, to improve the productivity, and reduce the produced waste. So the first trials was done at Halifax. So you can see this is the Halifax shipyard, and this is the ship that is supposed to be cleaned. It is the HMCS Ville de Quebec, and it is all wrapped up in tarps because they were going to clean it um, with the sandblast, and they didn't want it to um, pollute the environment. And they had onshore green tent. So you can see all of the lasers that we took there. They included the 100-watt, the 200-watt, and the 500-watt, plus the chiller, and also our BOFA cleaning system for cleaning the air. Basically, they were all in these boxes, and several operations took place. So one of them was onshore cleaning in the green tent with the 200-watt laser. Several objects were cleaned uh, in this area for rust and paint. Metal objects were cleaned, and I'll move on to other things. So one thing that was cleaned was the plenum of the ship. And I'll show you where the plenum is. You can see there's a raised structure here. And this is an area for air circulation and heating and air conditioning. And basically, what we did was we kept the 500-watt laser uh, outside on the deck, and the 22-meter fiber went into the plenum and started to clean different paints. So you can say that we also needed to do a surface profile for these paint removal. So for example, we managed to clean 30 centimeters square in 30 minutes with the 500-watt laser, and we made a 3.7 mil profile, or also 30 centimeters square in 10 minutes and left a 4.2 mil profile, depending on the thickness of the paint. So the plenum was one area, and the other area that was cleaned was the bilge of the ship, and that is the area which is at the bottom and is submerged into the water. So in order to get there, one had to route the laser system through hatches to the bottom of the ship from the deck, and the only laser system that would fit was the 100-watt unit that was carefully basically brought down through the hatches, and their space constraint played a big part. Rust and paint were removed. So this was a concern for the workers there, that it would be better to have a unit that could be carried by one person rather than several people helping to bring this unit down to the bilge. The This is the onshore cleaning. Yeah, in the uh, onshore cleaning that was done using a 200-watt laser in the green tent. And what was cleaned, a 6-inch pipe flange, removal of rust, and also same pipe removal of paint, or a similar pipe removal of paint. A bike frame was cleaned, grease on sprockets and welded plates, post weld cleaning to remove slag and spatters on bad weld and clean a good weld. So these are some operations that were attempted. It didn't really work well for slag and spatters, but it cleaned the rust and paint very well. And then in Shelburne, which is 200 kilometers away from Halifax, in their shipping, you can say, repair area, the 500-watt was used to clean flat surface of steel substrate from rust, heavy corrosion, rust on steel substrate on L-beam, and intersleek paint over steel substrate. And this was done very successfully in Shelburne. Typically, uh, about 100 nanosecond pulse width and uh, between 6 to 12 kilohertz of repetition rate was used for these. So what the conclusion of this was, uh, they wanted the managers and the workers, they had some suggestions that this is a very promising technology, but we need to reduce the size and weight of the laser system, and we should make it more user friendly and faster also. So you need to find the best parameters to use for different surfaces. All right, another case study. We have the testing at Canada Aviation Museum, where oil and laser engine parts are being removed. So these are some, you can say, operations that we did there. And then we also have the leaded paint laser cleaning. So lead is very dangerous, as you know, for health. So you cannot only use a HEPA filter, but you also need to use a BOFA filter that has several compartments in a circular form. So the heavier particles, they pushed by centripetal force, and they move towards the outside of the curved path where they come into contact with the steel scroll, and they drop down uh, in the chamber, which is within this filter. And then the rest of the particles, they go through the filter. The air flows through the filter media. So several stages of cleaning and filtering are done. So you need to use this to remove the paint. So let's look at the leaded paint laser cleaning. So I'll send you the video. So this one is case study. Which case study was this? Case study 4. So let me send you this. Control C, and I will share that with you. Control V, and I will also play it. Hi. Yeah. This is Mr. Zuckerberg. The hardest part of my job. So you can see different areas were defined here, and the 200-watt system is cleaning on a steel panel with lead paint. Okay, so next we go back to our presentation, and we look at, yeah, this is the polygon scanner. The polygon scanner is moving very fast and is generating all these lines, and a 200-watt system was used, 5,000 RPM, and this spray paint is being removed. So let me share that with you. Case study 5. Control C. Take a look at that. We'll also play that. So here you go. You can see how fast the polygon scanner is moving here, and is removing spray paint from this metal surface. Okay, so that's that. And next one, there was an interesting case for removal of weeds or thinning of crops. So, because of the shortage of labor, mechanical means and manual means are not available. So, these days in agriculture, they tend to use robotics, and laser would be a good fit in there. So spraying chemicals would be dangerous for the environment and could contaminate water supplies. So you can basically shoot the meristem of these extra plants or weed with laser. And we have done some testing on that. We have a customer in California that is interested in this. I'll show you a picture there, or a video of the operation. I'm not going to send it to you because this is a Google Drive uh, link. It's not a YouTube link. So, oh, at this time, this is not possible to open. So, sorry about that. We just basically tried our laser and removed the weeds by shooting at the meristem. So this was quite successful. So next we have application of laser cleaning for greasy and bacteria infected surfaces. So in food industry, this is very useful because uh, removing small particles that stick strongly to the surfaces is not an easy task. So the barbecue trays in the food industry, they're full of grease, and laser could effectively, a near IR could be absorbing by these sticky films and could basically blast them away. And there was also a paper on bacteria infected surfaces where they used several different types of laser, including CO2 laser and neodymium YAG at 1064, and it's at second and third harmonics, basically, at 355 nanometers. And they found that these sticky biofilms, which are not easy to remove using detergent solutions, are easily removed by CO2 laser, and also neodymium YAG laser at the fundamental wavelength did a good job at removing and cleaning these surfaces. So this one I'll skip. So in conclusion, what did we learn from this webinar? That laser cleaning is environmentally friendly, it reduces damage to the substrate, has a great selectivity by tuning parameters, does not require secondary medium, reduces health hazards to the operator, is less noisy, more economical as compared to other paint removal methods, such as sandblasting, dry icing, and chemical stripping, when all costs are taken into account. And we looked at different parameters of the laser that are important, and also material properties. We also compared the polygon scanners with the Galvo scanners, and we compared the CO2 laser in mid IR with near IR lasers, and we mentioned that although inherently CO2 lasers are safe, you can achieve the same safety by tuning the parameters with the near IR, and also they get the additional advantage of fiber optic usage with the near IR. A laser cleaning could zap meristem of unwanted plants and destroy them. It will be used in applications, for example, in thinning of crops and weed removal. And finally, we saw a case study in the shipyard where it could clean the plenum and bilge of a ship, and also in the repair workshop on land. For future, the modifications have been requested by shipping industry to reduce the size and weight of the laser controller box, laser head, and also Galvo, increase the size of the fiber optics, and increase the speed of cleaning by coming up with better recipes for cleaning different surfaces. So with this, we come to the end of our webinar, and thank you very much for listening. We'll send you a feedback form. In case you have any questions, please fill out the feedback form and send it to us. If you have any suggestions, I'll be glad to hear your suggestions how to improve the webinar. And at this point, if you have any questions, please feel free to ask. So you can either type your question, or uh, you can just ask. You can just unmute yourself and ask. Hello,
Right.
Andreas. You have a question?
Hi, Rez. Yes, I have a question. I'm a materials engineer working in aerospace, and obviously I'm interested, in aerospace applications. I've
Yes.
seen that you've used the laser cleaning for removing paint in aerospace.
Yes.
Is this application quite advanced? So has it been studied in some detail? Because I'm, I'm not too much in that in this issue in this scientific background of this laser cleaning.
Yeah.
So, but for example, what is the temperature if I'm removing paint from an aerospace surface?
Mm.
So yeah, we are obviously concerned about the impact it has on the metallurgy
Mhm.
side of things of
Yes.
the aluminum and
Yes.
so how shall I put it and on the handling the handling issue, how can it be applied to an aerospace by the staff without
Right.
damaging the surface?
Right, right. Actually, it's a very good question you're asking because I want to show you a video where actually a fuselage of an airplane is being cleaned by the laser
Mhm.
cleaner with a very heavy robot that is holding it. So that may answer some questions. So let's go to Allied Scientific Pro YouTube channel, and here is the YouTube channel, and
Mhm.
introducing the new and improved Lighting Passport, the world's first smart spectrometer. Not this one, the videos. Yeah, this one you can see. Let's stop this for a second. Yes.
Okay, so
So you see, this is a part of a fuselage of an airplane, and this is our Fanuc robot that is holding the laser cleaner, and it is shining it on the fuselage. It's holding it at the focal distance.
mhm.
I can share this video with you, and I can
Yeah.
actually ask our engineers to provide you with more information because I already have your email.
Yes.
So you have questions about temperature and how to handle it and so on, right? Is it
Yes. Yes.
possible for you maybe to send me an email with all your questions, and then I can give you accurate answers about each one.
Yes, of course. Yeah. I
Yeah.
would
So
like.
I'll share with you this video also, so you
Yeah.
can
Thank you
look
very
at it.
much.
Yeah, you're welcome. So uh, because you need to adjust the parameters very well, so maybe not use too long pulse width, but at the same time you want to have a speed. So
Hmm.
make proper adjustments of the energy, the pulse width, and the repetition rate. And our engineers have some recipes for aerospace for cleaning aircraft body parts. So if
Hmm.
you send me an email, I can provide you with more information about what needs to be done, and what it takes and what temperature it will reach.
Hmm. Yeah, very good. Thank you for that, and I will send you an email. So I think your email was provided in the
Yeah. Oh,
laser cleaning site. I think the introduction to this webinar. So I will.
yes. I'll also type it here for you.
Very good.
Armani at AlliedScientificPro.com here. So you
Right.
can copy that if you like.
Yeah, thank you very much indeed.
And
So
where are
I
you
will.
located? May I ask? Where are you located?
Close to Munich, Oberpfaffenhofen.
Oh, right,
It's
right. In
called
Germany. Okay.
in
Oh.
Germany, yes.
So what
So
kind of aircrafts do you handle?
yeah, it's like 19-seater, yeah, Dornier aircraft. So yes,
Okay.
prop aircraft and
Prop aircraft. How many engines does it have?
two.
Two engines. Okay. Prop aircraft. Yeah, that's very interesting. Very interesting
Yeah.
application. And in my talk also, I talked about the Canada Aviation Museum. Let me show you that. I actually skipped that. I can show it to you now if you like. Testing
Hmm.
at Canada. These are some engine parts that were being cleaned of grease and soot. Okay.
All right.
So for example, let me go there and I will just the laser cleaning sandblasting. What case study was this? Just a minute. Case study 3. Okay. So case study 3, yes, here. So let me send you this. I'll send you this, and we can also play it. You can see. Do you also need to clean some engine parts, or you only need to clean the body?
Um, I mean, we are looking quite broadly at it at this very moment. So I'm more into paints and corrosion removal. But
Right.
if it's, I could also present it to my colleagues, and they may be interested in doing other things with it. So
Yeah.
yeah, so it's generally at the moment we are trying to get acquainted with new methods of cleaning and yeah,
Yes.
paint removal and corrosion removal and yeah,
Yeah.
to have
Yeah.
new
Paint and
ideas
corrosion.
and
Yeah, paint and corrosion I understand, but I'm asking, do you have any application like this as well, where you need to use to clean oil or soot from some engine parts?
uh, I would um, certainly think so. Yeah, most definitely we have some applications like this. I'm not a aircraft systems guy. I'm more into the structural things and paint. But yeah,
Hmm.
I know I'm sure there will be applications like this in the maintenance we're doing and where we have to remove such stuff of engine parts. And yeah, I'm quite sure.
Very good.
So
And what company? What is the name of your company? May I ask?
General Atomics. So in yeah,
General Atomic.
yes.
Can you type it? Can you type it?
So I can send you.
Like
Uh,
there's a
let
type
me see.
button there. There is like a chat button. General Atomic. Let me see if I can find you. Andreas
Um,
Daner. Right, right. So
yeah. Well,
danersa
just a
at
moment.
gmail.com. Okay, okay.
Where can I?
There
Ah,
you
yeah.
see on the top right corner, top right,
Ah,
there
I
is, you
think I
can
have it.
see like a settings. It's like a gear, and right next to it there is like a dialogue. It's a circle with a little thorn on its side. And if you click on that,
Yeah.
you see my
I
screen.
think I'm. Yeah, I think where you've put. I think the chat and where you put all the YouTube videos. I think I can reply there, can't I?
Yes, that, yeah,
Yeah.
exactly. Exactly.
S- um,
So you can just type in the box and send to everyone. Okay, General Atomics, Aerotech Systems. Oh, excellent, excellent, excellent. So I understand this GmbH is like ink, right? In English. Is that true?
Uh, I'm not so
Yeah,
acquainted with the yeah business forms in
right.
the US and the equivalent in Germany. So, but it's
Yeah,
something like this, yeah.
exactly. Like
So this is a
incorporated, the short for incorporated. Because I was
yes, and
wondering why all
and
these companies, German companies, have GmbH, and at some point I did a search and I found this is like the ink, equivalent to the ink.
yeah, something
All
like it.
right.
Yeah.
Yeah, okay, great. So
So
very
yeah,
nice
I will
talking
send.
to you. Yeah, and send me the
Yeah,
questions. I'll get back to you on that, okay?
right, brilliant. Thank you very much indeed, and thank you for your presentation.
Thank you
Thanks.
so much. Thanks for
Bye.
attending. Have a great day. Bye. All
Yeah,
right.
bye bye.
So that's it. Bye. Goodbye. Thank you, everyone.
Goodbye.
Bye.